Welcome back, guys. Today I'll be talking about Gaussian distribution, more popularly known as normal distribution. And over here we have x random variables, and we find PDF because it's a density distribution. Continuous random variable x is said to follow a normal distribution with parameters mu and sigma square if its PDF is given by f of x equal to 1 by sigma root of 2 pi, where x is between minus infinity to infinity, mu is again the same, and sigma is greater than 1. First, we find mean and variance by expectation method. Right. Initially, we start off with e of x, which is basically f of x, integration of f of x with respect to dx, and this is again expanded as follows, where f of x is expanded as follows, and 1 by sigma root of 2 pi is taken out of the integration. So let x minus mu be y, and d of x is equal to dy if we differentiate that. So on doing that, we get the following function. And right now we take the integration, which we simplify exponent. We rewrite the equation in the following manner by taking y and mu by 2 sigma square common, root of 2 pi common, and this while substituting y square is equal to t, we get, and differentiating it, we get 2y dy is equal to dt. And now we substitute that in the equation. So on doing this, we get f of x is equal to 1 by sigma 2 pi root of 2 pi exponent minus x square by 2 sigma square. On integrating f of x dx from minus infinity to infinity, we get 1. So ex can again be written as the follows. I mean, this is why statistician is probably the most boring job until machine learning came along. Now it's officially the sexiest. Girls, you can find me on Tinder when you do swipe right. So e of x can finally be brought down to mu because of the following simplification. And on expanding it, we get the following. Therefore, because f of minus x is equal to minus f of x for odd functions, we for a definite integral, we get it as 0. So therefore, e of x is equal to mu. Now variance x, v of x can be given as e of x, x minus e of x inside that whole square. So this can again be simplified as x minus mu because we already proved that e of x is mu. And we follow the same process again, where we take integration minus infinity to infinity. The normal distribution is probably very important, all thanks to central limit theorem. You can check out a demo of central limit theorem over here. I mean, think about it. So, not most of y'all would have, not many of y'all, like very few of y'all would have closed the video in the beginning itself, right? And most of y'all would have gone through half of it. So that's most of y'all. And very few of y'all who really want to learn and succeed would have gone through the entire video, probably even liked and subscribed. And this basically is normal distribution. So on here we put t square as theta, so we get 2t as dt, 2t dt is equal to d theta, and on integrating dv we get e to the power minus theta by 2 with respect to d theta, and v is equal to minus 1 by 2 e to the power minus theta, and 2 sigma square by root of pi, we substitute this as v, so we get v in terms of minus infinity to infinity minus integration of minus infinity to infinity v with respect to du. This is further simplified as follows. So this on simplifying it, we get e to the power minus t dt, and on further simplification we cancel out 2 and we get the following. We take this integration is equal to root of pi for Gaussian integral, and v of x is equal to sigma square. Now next we find moment generating function. For moment generating function we take mx of t, which is again e to the power tx. We integrate this as follows: fx of t. Now we expand fx of t as given before. We get sigma out of this equation. And on substituting dx by sigma is equal to dv, we substitute x minus mu by sigma square is equal to v and differentiate that to get dx by sigma is equal to dv, and we replace that in this function. E to the power tu plus t square sigma square by 2 whole divided by 2 pi is outside this integration, and the remaining part of the integration is given below. So definite integral for even function is given as 2 from 0 to infinity f of x dx. V of v minus t sigma is equal to mu, so we take dv is equal to du, that's equal to that we substitute again. There's basically integration by substitution, which happens quite often in this proof. Now we put u square by 2 as theta. So on differentiating it, we again get 2u du by 2 is equal to d theta. And we again substitute, integrate it further. And this is like the simplest form where we can actually integrate it. So that is 0 to infinity e to the power minus t 1 by root theta d theta. Now we take root theta from the denominator and put it all up in one equation, and this is simplified as e to the power tu plus t square sigma square by 2 and whole thing divided by root pi, because integration of 0 to infinity x to the power n minus 1 e to the power minus x dx is equal to root n, and this equates to e to the power minus tu plus t square sigma square by 2. That concludes the equation. So finally we go for moments with respect to mean. So for moments with respect to about mean, we get mu1 is equal to e to the power minus mu t et e to the power tx. Now again, e to the power tx is put in expanded as follows. No, we get e to the power tx because of this following method, and e to the power tx is again expanded in the form which we did before for the multiplication of this exponent function is simplified as given, and mu1 is equal to 1 plus t square sigma square by 1 factorial, and then by 2, and then by 3. This gives coefficient of t to the power r by r factorial, gives the rth moment in the same form. So mu to the base 2n plus 1 is equal to 0, where n is equal to 1, 2, 3, and so on, 0, 1, 2, 3, and so on, for every order moments. Now, coefficient of tr to the power n by 2n factorial is equal to the follows. So basically this function ends as follows on expanding the factorials.